All right, so we've started recording, so hopefully that's working. All right, so hello and welcome to the CVEN3401 Sustainable Transport Engineering Crash Course. So we hopefully will have good attendance online in the video. There's like 2 people in the room right now for anyone joining in the video, but that's all right. Okay, so here we've got the, I should have put this up before, sorry. I'll put it up now while I talk a bit. So I've got quite a few QR codes here. If you're watching, just pause the video. Obviously, if you're watching, you can ignore the top 2, but the bottom 2 are really important. So how I've done this is, the bottom left one is a QR code for the midterm. If you guys can let me know if it works, it should go to my OneDrive and then you should be able to see it. And that's just the questions, so that when midterm comes around, you can just practice the questions. I retyped it up even, so that it's like a bit neater. It's an online midterm, so I removed the solutions. And then on the bottom right is this crash course, including the midterm answers. So if you're watching this right before your midterm, which is probably what you're doing, then I would recommend do the midterm, try it out, and then you can watch this crash course, and you can see me go through the answers. All right, I think everyone got it?
Yeah.
Did those QR codes work? They should work. Well, okay, I'll just keep going. Let me know if you want me to come back to this. Okay, so these are some of the things that we'll be learning about in transport. So traffic flow equations, trip generation models, utility equations, highway design. There's a lot of things in this course, so it's probably easier for me to just kind of go through the content. I think it's a bit of a, it really is an introduction to transport. Like, it goes through everything. And then there are courses, if you really like transport like I did, there are courses like electives that will then dive more into each of these. Like, for example, CVEN3401 kind of dives more into that, and then CVEN9401 dives more into that one, and also this one, the 2 middle ones. But I'll give you a bit of a rundown on my general advice for this course. So I would actually say this is a reasonably challenging course. Even as someone who really likes transport, I actually found it I'd say medium difficulty. So it's the type of course where I would say harder than steels and concrete. Steels last year. I hear steels was a lot harder this year, but harder than the structural courses for me, but then probably easier than soil mechanics. I actually think soil mechanics ended up okay. So maybe even not that much easier than soils, to be honest. So the point is, it's reasonably difficult, so you can't just put it at the back of your head. I actually did better in concrete. I did concrete and this at the same time, and I did better in concrete, even though I put way more time into this, which is kind of baffling, not gonna lie. I think what makes it hard is that even though the material is relatively reasonable, Divya, who will be your lecturer, kind of makes the exams difficult from my experience. I've done 2 subjects with her, so I'm gonna just check it's recording. Yeah, I've done 2 subjects with her, and that seems to be pretty universal. She can make the content hard, but she is a good lecturer, so you get what you put in. She'll answer your questions if you email her. She's pretty friendly, and she's quite motivated in terms of making the lectures make sense, but she just makes exams hard. It's the main point. So yeah, just do the practice questions, watch lectures, and you'll be fine. Great. Hello. Okay, so we'll go through last year's midterm today. So it's worth 25%. It's entirely online and open book. Wouldn't say this makes it easy. I found it pretty challenging when I did it. Fortunately, your working out is marked, so it's not like those annoying Inspero exams. And having done 2 courses with Divya, she doesn't recycle as much as other lecturers. She still does, so that's why you should still definitely do the past papers, but I wouldn't say she really recycles as much. So definitely practice as much as you can beforehand. Try to actually understand the content rather than just memorize questions, because it'll just make it much easier. It's just it's like structural engineering in some ways, but it's a bit more thinking, I guess. I think with structural engineering, with steels and concrete, you're kind of following a template, you're following rules, With this, you kind of are as well, but there's extra layers of thinking, and it's not as much of a what applies to this question applies to that question. I think in that sense, it's a bit more like kind of like geotech, if anyone's done that yet, like soils. Okay, so let's start going through the midterm. And while I go through the midterm, I'll also teach you the concepts, because of course you haven't learned any of this yet. So this is question 1, okay? So this is the first part of the question, which is, so you can kind of ignore the first 2 lines, but the speed and density data collected for Avenger Street in Schofields is presented in the table below. And that is the survey data for Avenger Street. So basically what's happened here is we've been given a bunch of cars that are going at a particular speed, and what's the density of the vehicles, all right? So for example, there are 11 cars going between 0 and 10. So, okay, actually no. So when the vehicles are going between 0 and 10 kilometers an hour, there are 11 of them that are doing that, and there's 105 vehicles per kilometer, okay? 10 to 20 cars, there are 31 vehicles going between that speed, and the density is 87.5. So I actually think it'll make more sense if I kind of try to draw this out. We got more people coming in. All right. So let's draw it out like that. Okay, so basically, as the speed goes up, the density of vehicles is also going up, okay? And so that speed, actually probably speed would be on the other axis, wouldn't it? I have some graphs later on that I'll show you that'll make more sense. And this is speed, okay? So this is it's kind of a linear relationship. I'll show you here. So speed and density have a linear relationship. So what this is saying as the cars are going, oh, actually no, it'd be the other way around, sorry. It'd be downwards. So when the cars are, oh no, is it up? Sorry, let me check. It is down, yeah, it's down. So it would actually be speed and density. So I'm gonna replot it. So you'd have speed up here, and I'll try and explain it to you, and then we'll read through the question. Okay, so if you think about a road, okay, so what density means is how many cars there are per kind of kilometer, okay? So actually I'll move that there. So let's say this would be a low density, okay? If we had like 1, 2 cars, okay, that's low density. And then if we have like 100 cars or something, that's high density, okay? So intuitively we know which scenario the cars are going to go faster. It's going to be this one. Cars are going to go faster when there are less cars. When there are more cars, cars are going to go slower. So that's what this graph is kind of illustrating, okay? So for a road like Avenger Street, the faster the cars are going, the faster the cars are going, the lower the density, okay? And then the slower the cars are going, the higher the density, okay? So if there's a lot of cars, obviously the cars can't go as fast. If there's not many cars, then the cars can go a lot faster, okay? So that's what that relationship is showing, okay? So part A is calibrate a Green-Shields model explaining the linear relationship between speed and density. Provide the following. So the dependent variable, the explanatory variable, and the coefficient of the explanatory variable. And then we'll go through part B, C, D, and E afterwards. So this question is a lot to take in, and when I first saw it in the midterm, I was like panicking because it's like a huge question, and it's worth 5, 6, 8, 9, 10, 15 marks out of, I think the midterm was out of 40. So it's like almost half of the exam or something like that. But I'll explain to you the fundamental concepts that will actually allow you to do this question. Okay, so first of all is flow, all right? So this is one of the first things you'll learn in this course is the equation for flow. So the equation for flow is basically Q equals the number of cars over the period of cars times 36,000 seconds over hours. So for example, if we said that on a freeway, we had 300 cars, okay, past us. So let's say I'm standing on a road and 300 cars passed me in, we'll say 0.5 minutes, okay? 0.5 hours, I'm sorry. Okay, so time interval, so we're taking t to be in hours, okay? So 300 cars pass me in 0.5 hours. Intuitively, you know, even without this equation, you should know that Q equals 600 cars per hour, or you can convert it to, let me get my calculator. Or you can convert it. So it would be, well, it would be 600. It would actually be 600 divided by 0. So it would be 0.167 cars per second. Okay. So did I do that equation wrong? It might be flipped. It might be 3600 over. It might be 1 over 3600. Anyway, let me think. N over t times so the number of cars passing a given point in t seconds. Oh, it's in t seconds. Okay, that's why. Okay, yeah, sorry. I've got it the wrong way around. So the equation is from seconds to hours. Okay, so I'll redo it because I kind of read it wrong. So say you had 3 cars pass you. Bye. See you, Henry. Say you had 3 cars pass you in 60 seconds. Okay, so that would mean 3 over 60 times 3600. It would mean 180 cars would pass you per hour. Okay, so that's flow, right? That's Q. Then we have density. So density, I kind of already went over this. It's the number of cars within a given road section. Okay, so for example, if you had 3 cars in 2 kilometers, then that would mean the density, that would mean the density is 1.5 cars per kilometer, okay? So density, it's like very different to what we're kind of used to, like in physics and stuff. We're obviously used to density being like, you know, the density of a liquid, the density of but this is density of a road. So it's how many vehicles per length. Now, this equation is incredibly important. It's the flow speed density relationship. So it's Q equals KVS. So that is the flow of a road is the product of the road's density and the speed of the road, okay? Which hopefully should make sense, because if you think about it, like, the cars can move as fast as the road's density allows it to. All right, so time mean speed and space mean speed, these are important. The question doesn't actually go over it, but it's just something that's important to know. So I'll talk through it with using an example. Okay, so let's say we had 5 vehicles that are going at, we'll say 60 kilometers an hour, 65 kilometers an hour, 67 kilometers an hour, 68 kilometers an hour, and 70 kilometers an hour, okay? So the time mean speed, okay, this is literally just the average. It's just the arithmetic mean, okay? So it's just 60 plus 65 plus 67 plus 68 plus 70 over 5. You all know that. I'm not even going to find that. But space mean speed is technically a new one. You may remember harmonic speed, harmonic mean from like high school or whatever, but it's kind of the inverse, the reciprocal. It's 5 over 1 over 60 plus 1 over 65 plus 1 over 67 plus 1 over 68 plus 1 over 70, and that will equal whatever. It will always be bigger than time mean speed, okay? So that's something important to remember. Or smaller. Let me just check which one it is. Let's see, so 60 plus 65 plus 67 plus 68 plus 70 over 5. So that's 66. And then 5 over 1 on 60 plus 1 on 65, 1 on 67 plus 1 on 68 plus 1 on 70. And that is, sorry, it's always smaller, my bad. I had a feeling I got it the wrong way around. So it's always going to be smaller than time mean speed. Okay, so those two are pretty straightforward concepts. You might be asked it might be just like 1 or 2 marks. Just remember which one's which. That's why it's good to have a formula sheet. You can also just look at my notes. So Greenshield's model. So this is a specific equation that you can use that assumes speed and density have a linear relationship. So as density goes up, speed goes down. As you have more cars on a road, obviously the road's going to go smaller. And this is the relationship that we are given. So basically the speed of the road, Vs, is equal to the free flow speed minus Vf over Kj times K. All right, a lot of things to take in there. Vs is just speed, Vf is free flow speed, and K is density, which just basically means how many vehicles are there per kilometer is usually what we would say, okay? So to kind of try and understand this, and just before we do, make sure you only use this equation if the question says the traffic obeys the Green-Shields model. So I've been caught out in the past because, so Green-Shields model will come, if you choose to pursue transport engineering like I have, it comes up in other subjects, and I've made the mistake too many times of you assuming we can use this equation when you can't, because it doesn't apply unless it obeys Green-Shields model. So just make sure you only use it if it obeys Green-Shields model. I mean, it would be like trying to use a linear equation for a parabola. Like, you need to make sure it's actually a linear equation. Okay, so these are some of the ways that we can rearrange Green-Shields models to kind of give us a few more interpretations. And you can look at this a bit more later, like the equations I have there. But basically, we've got VF, and so basically this is speed and density. So the higher the speed, the lower the density. I've already kind of explained that one. But this one is an interesting one here. We've got the relationship between flow and speed. Okay, so think about if we have zero flow, that theoretically could mean, zero flow can mean two things. Zero flow can mean there are no cars on the road, so it's literally empty, or it could mean there are too many cars on the road. So it's quite an interesting like paradox. Okay, so it can mean there's no cars on the road, so that means there's nothing moving, no cars. It's no cars, or it can mean too many cars. Okay, you think about a traffic jam, too many cars. Okay, and then in the middle, between those two, we have the perfect scenario where we have not too many, not too few, we have maximum flow. It's like the Goldilocks, okay? This is maximum flow, max flow. And again, this only holds if it's Green-Shields model, okay? So you can't apply this in every situation. Yeah, okay, and then we have this one, which is the relationship between flow and density, and you can see it's quite similar. Again, you can have zero flow either if there's too many cars or too few cars. It's the exact same thing, no cars, that means no flow. And too many cars means, again, no flow as well. And once again, you have maximum flow at half of the maximum density. Okay, theoretically speaking, every road will have a maximum density where you genuinely cannot fit any more cars. Okay, and these equations are going to help us with this question. All right. By the way, since so many people have just arrived, I should go back to the first slide. So I'll take a moment, and anyone who's watching can fast forward this part. So I have so there's the attendance form. I can put that up again later, but maybe what will be more important is if you want to follow along this course, the bottom right has this crash course, including the answers. So it's just this PowerPoint. Then the bottom left is just the midterm, which I've made specifically so that when it's the midterm, you can practice. So by midterm, I mean 2025's midterm. It'll probably not be the same. I think she'll change it. I'll give you a moment if you want to scan that. And if you're watching, just fast forward. Okay, I think that's enough time. All right, so let me know if you want me to come back to that, otherwise I'll keep going. All right, so I explained Green-Shields model to you now. Hopefully that makes sense. Okay, I actually do want to quickly explain a little bit more before we continue to the question, which is basically the concept that what actually is free flow speed. So free flow speed is what speed the cars can go at if there's no cars. Okay, so if you think about it, K is density, okay? K is how many vehicles are there per kilometer. If there are no cars, that is free flow speed. That is like the fastest the road can be traveled on. All right. Okay, so when this is zero, then the speed of the road is equal to the free flow speed, okay? Which we will need for this question. Okay, so we're gonna do part A. All right, and so we've been told to calibrate a Green-Shields model explaining the linear relationship. We need to provide the dependent variable, explanatory variable, and coefficient of explanatory variable. So this is the Green-Shields equation, all right? So the answer for part I is the dependent variable is always the one on its own, for which in this case is speed, okay? So it's just Vs, all right? And the independent / explanatory variable is obviously just going to be the other one, which in this case is density, okay? So in this case, it'll just be K. Not much more to it, and then Vf is just a constant, okay? Coefficient of explanatory variable is quite a pain to find, so I will talk you through it. I think this is pretty hard. Definitely hard to go through in the very first thing you do, but I'm going to talk through it anyway because it is in the midterm. It was in the midterm last year, that is. Okay. So basically, we've been given all of this data, all right? And what we're trying to do is we're trying to fit this data to that equation I've been trying to talk to you about, okay? This equation. We want to plot it on a graph, okay? But we've been given a crazy amount of data, okay? This is a lot of data, and so Divya actually has a specific way that she teaches to kind of fit it to that data, and it's like a really complicated statistics thing, but I will go through it just so that you guys understand. Okay, so we use the following rather long equations from the lectures, where V is mean speed and K is mean density, all right? So, all right, so basically remember that the Green-Shields equation is Vs equals Vf minus Vf over Kj, was it? I think, yeah, Vf over Kj, K. Okay, and we're trying to basically just fit this data to that equation. So the way we do it is we're just told these equations. So B equals n times the sum of K times V minus the sum of K times the sum of V over, I'll just zoom in a bit, over n times the sum of K squared minus the sum of all of the K squared. Okay, let's check we're still recording. Yep. And then A is the average of the speed minus B times the average of the density. Okay. And then the Green-Shields equation is just A plus BK. Okay. So unfortunately, this equation is a pain to use. Just refer to it if your midterm has a question with frequencies. So you probably won't need to if there's no frequencies, but the way this question is written is you're meant to reuse this equation. And I don't think many people got this one last year. I actually didn't get it either. I've just like gone back and redone it so that you guys can do it. So basically what we're going to do first is we're going to find A. Okay, so A is the average of all the speeds minus B times the average of all the densities. So what we have is V is going to be 5 times, so we're going to set this to be the midpoint. So the midpoint of this one's 5, 15, 25, 35, 55, 65, 75, okay? Okay, so 5 times 11, 15 times 31, 25 times 14. So the average ends up being the sum of all of these over, I mean, you guys know how to find averages, I'm sure, so hopefully that makes sense. It equals 40.723. And then K is the exact same thing. It's just 105 times 11 plus 87.5 times 31 plus 32.5 times 14, etc., blah, 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 over 11 plus 31 plus 14 plus 29, blah, 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 all the way to until you get 55.602. So we now have A nearly. But the weird thing about A is to get A, we actually need it to be V minus BK. So we actually need to find B first. Okay. So we'll find B now. So B is N times the sum of K times V. Okay, so K times V is going to be 105 times 5 plus 87.5 times 50 plus 72.5 times 25 all the way down to the bottom. And N is just the sum of this. Okay, the sum of that is 166. Okay, and if you do all that, you should get this crazy big negative number. As for this one, it's a very similar thing. It's N times the sum of all the K squared. So 105 squared, 87.5 squared, 72.5 squared, all summed up. And then you add them all up for this one. Okay, so 105 plus 87.5 plus 72.5, blah, blah, blah. And then you square the sum. Okay, and you should get 231,698.25. Okay, and then from this nightmare, we get B equals minus 17, well, blah, blah, blah. We get minus 0.76. Okay, and then A is the average of V minus B times the average of K. So you get 82.98 to be A. So finally, after all that, we finally get Vs equals 82.98 minus 0.76k. And remember that we identified density as the explanatory variable. So it's asking us for the coefficient of the explanatory variable. Density is the coefficient, so the coefficient is going to be minus 0.76. Okay, so it's quite rough, but if you can understand this, this is probably one of the hardest in the midterm. So if you take the time to understand that, you should be all right. And I'll just kind of, I guess, quickly explain to you what that means. That basically means that you can calculate the speed of the road based on how many vehicles there are. So if there are 20 vehicles per kilometer, then we use this equation, okay? So say there are 20 vehicles per kilometer. That means the speed of the road is 82.98 minus 20 times 0.76. 82.98 minus 20. And we end up with 67.78. So that means that if you have 20 vehicles per kilometer, the road is going at about 67.78 kilometers an hour. All right. And then if you were to plug in like 100, then you'd probably get a really low answer. And then if you go too high, you get 200, you'll get a negative answer, which means it's not possible. That means you've gone too far and you've reached the maximum number of vehicles the road can carry. Okay, so we'll continue now. Any questions so far? No? All right, seems like everyone's good. Okay, so I've now written out this equation. This is the equation of the line. So determine the free flow speed and jam density. Okay, so this is now that we've done part A, part B is a lot easier. Okay, so this is where I encourage you to kind of just think and like go to first principles. Okay, so free flow speed means what speed can the road go at if there's no one on the road, basically. It basically means the maximum. Okay, so you think about like if you're driving at 4 a.m. at night, like you can go at whatever speed you like because there's no one on the road stopping you. If you're driving at 9 a.m., on the other hand, you have to go slow because there's lots of cars on the road at that time. Okay, let me just check. Okay. So I've had OBS glitch before, so I'm going to keep checking. So basically, if there's no cars, you just set K to 0, and then you know it's going to be 82.98. Okay, so the free flow speed is 82.98. So I encourage you to try and think about it first principles, but otherwise, you know that the equation is in the form Vs equals Vf minus Vf over Kj times K. So, you know, Vs is Vs, K is K. So you know Vf is just going to be 82.98, okay? And then jam density means, so again, just think about what jam density means. Jam density, jam literally means traffic jam. Like, it means it's jammed. It means no one can move, okay? So all we do, if no one can move, that means speed is 0, okay? So we set Vs equal to 0. Oops, I'll use a different pen. Okay, so that means 0.76k equals 82.98. So k equals 109.18 vehicles per kilometer. Okay? And that's the jam, that's the maximum. You can't fit any more cars on the road. All right, I think we're good. Okay, so now we have Vs equals 82.98 minus 0.76. Oh, sorry, why am I reading that? I meant part C. Okay, part C is determine the relationship between flow and density, and then part D is determine the relationship between speed and flow. So this question, what we've done is we found the relationship between speed and density. So we now want to find the relationship between flow and density. So answer for C, there is no flow component in this equation, so we substitute in the fundamental flow equation. Okay, so remember, Q equals KVS. And we're trying to shove Q into this equation somehow. So if Q equals KVS, that means Vs equals Q over K. Okay, because of course, what we're trying to eliminate, okay, we want flow and density. We're trying to eliminate speed. Okay, we don't want speed there, so that's why we sub in Q over K. Okay, so Q over K equals 82.98 minus 0.76K. Q equals 82.98K minus 0.76K squared. Now, if you check the question, it wanted us to find the values of C1 and C2, okay? So you can write that C1 is 82.98 and C2 is 0.76, okay? Part D is exactly the same. Part D is we want a relationship between speed and flow, okay? So if we go back to this equation, speed and flow. So we got speed, but we don't have flow. So we somehow want to get rid of k. All right, so we know q equals k vs. So just rearrange it and you get k equals q over vs. So sub in k equals q over vs. Vs equals 82.98 minus 0.76 q over vs. Vs squared equals 82.98 vs minus 0.76 q. 0.76 q equals 82.98 minus vs squared, and that's it. So q equals 109.18 vs minus 1.32 vs squared. Okay? So if you wanted to be pedantic, C3 equals 109.18, and then C4 equals 1.32. Oh, minus. So you got to be careful, it's minus. Okay? So part C and D, if I go back, they were worth 2 marks each. Part A is 5, part B is 3. Okay, so we've kind of done the hardest parts already. I'll leave it there for a moment, and then we'll do part E. I think we're good. Okay, should be enough. I think everyone's written it down. So, part E, okay, so we now have 3 equations. We have Vs equals 82.98 minus 0.76k. We have Q equals 82.98k minus 0.76k squared. And we have Q equals 109.18 Vs minus 1.32 Vs squared. So part E is determine the maximum flow, Q max, and density at maximum flow, K. Okay, so I've decided to go through this 2 different ways. So for starters, a little shortcut that you learn a bit further on in transport is density at maximum flow is also known as critical density, or KCR. So that's how I like to write it. I like to just write KCR. Critical density, the reason we call it critical, because it's the density at which you achieve maximum flow, okay? Because it's a balancing act, all right? As I've kind of already said earlier, if you have too few cars, then yes, all the cars are going at a good speed, but like there's just not many cars getting through. And if you have too many cars, then they're all getting jammed, okay? So every single road, theoretically speaking, will have a value where it's like perfect. It's the perfect number of cars to get maximum flow without causing a traffic jam, all right? And we want to find out what that flow is and what that density is. Okay, so there's 2 ways to do this, okay? We're looking for maximum flow, all right? So we have maximum flow and the density at maximum flow. So we know that Q equals 82.98 minus 0.76k squared, okay? So find the first, it's just high school maths. We basically just want the maximum of this equation, okay? So the derivative is 82.98 minus 1.52 KCR. Okay, I've put in KCR because, well, actually it should just be K. I haven't made it 0. So it would be, if this was 0, then it would be KCR, okay? So when Q dash equals 0, 1.52 KCR equals 82.98. So that means that KCR is equal to 54.59. Or to put it simply, when you have 54.59 cars per kilometer, you will have maximum flow. All right, sub that back into our original equation, and you will get that the maximum flow is 2265.03 vehicles per hour. Okay, I should have added units, and this would be vehicles per kilometer. Okay. So that is the first principles. Yep.
So in an example, we always round down the amount of vehicles, or will they just ask the exact?
She'll usually give you how many decimal places.
They should tell you.
She'll usually tell you, yeah. In this question, no, she didn't. Oh, she did, yeah. She actually did. So here it says, provide all answers to 2 decimal places. I know, it doesn't make sense because you can't have like 0.5 of a car, but I think she just prefers you to be exact.
Yes.
So she'll tell you to round to 2 decimals. So yeah, but rounding will come up a bit later on actually. It can be important. Okay, so that's how you do it by first principles. Otherwise, we can think about this for a second and do it much faster, okay? So, like, I mean, I always encourage people to try and think of things in first principles basis, because if you can understand the concept rather than just plug it into equations and formulas, then you'll probably be better braced for like if there's a curveball, which that's the thing, like what I'm trying to emphasize is Divya loves curveballs, having done 2 courses with her. So that's why it helps to actually understand it. So if you remember from earlier, I was telling you in green shields, critical density is at half of jam density. Okay, so I'm going to go back and show you. So if we relate flow and density, okay, you can see this is where we have too many cars. Okay, all right. As density goes up, you're getting more cars through the system per hour until we reach a maximum point where we start to have a traffic jam, and then we reach too many cars. But it just so happens that because it's a linear relationship for green shields, that the maximum flow is at half of the maximum density. Okay, so KCR equals KJ over 2. So you save a lot of time when you do that. Okay, and if you look at the derivative, you'll understand why, because of course, okay, I'm not going to bother explaining. I'm sure there's a reason. I don't want to have to go through that. So, since jam density is 109.18, critical density is just going to be half of that, which is 54.59, and that is what we got. Okay. Then we just sub this. So then we just sub this in as before to again get Q max equals 2265.03. All right, and then that saves us from differentiating. Importantly, this only applies in green shields model, so you can't just apply this assumption to any model. So just be careful. I've made that mistake before. Okay, and that is question 1. Any questions? You good? All right.
Do they give us any of these in the final? Like the first half, they say they don't give any formulas for the final. Is that true? Or?
Yes, that is true. Yeah. So actually, it's a good thing to talk about. So while we're kind of looking at this, so Divya will give you formulas for the midterm and formulas for the assignment. Well, the assignment, I'm assuming she runs it the same as last year. If she doesn't, that's another story. But last year, it was a midterm where it was like a 2-hour midterm. It was open book because it was online. The assignment obviously is a take-home assignment, so obviously that's open book. But then she made the final closed book, which made it a lot more annoying. Yeah. I think it definitely makes it harder. So keep that in mind, yeah. And that is one key difference with the structural courses, because structural courses are usually open book. So you can take in whatever you want, and then if the question's the same, you can just copy that. But sadly, you can't for this course, which makes it a bit more irritating. So keep that in mind. Okay, I think we can keep going. Okay, so question 2. So we'll read through it. It's on the left. So this is the question, and then this is the content, and then these are the questions. Okay. So the Southwest Sydney Transport Study has been divided into 4 large districts. The following data has been compiled to understand the trip distribution throughout southwestern Sydney area. Okay, the relationship between travel time and the friction factor associated with traveling from one traffic zone to the other is described in the following table. Okay, so before we continue, I'll try my best to explain what this means to you. Okay, so, okay, for starters, what this is it's trip generation. Okay, a very important part of traffic engineering. Okay, so productions and attractions. Okay, so say we have four zones. It might help us to actually have let's pretend to give them names. Okay, so we'll say this is Bankstown, Liverpool, Cabra, and we'll say Fairfield. Okay. So, what this is saying, and we'll say, well, I'll put it here too. Livo, Cabra, Fairfield. Okay, so this probably will help a little bit. Okay, so what this is saying, obviously it's not going to actually be accurate. It's saying that to drive from one part of Bankstown to the other on average takes 5 minutes. To drive from Bankstown to Liverpool takes 8 minutes. To drive from Bankstown to Cabramatta takes 12 minutes. To drive from Bankstown to Fairfield takes 15 minutes. Okay, to drive from Liverpool to Bankstown takes 8 minutes. You get the idea, okay? Or to Cabramatta to Bankstown is 12 minutes. Fairfield to Bankstown is 15 minutes, okay? So these are zones that we've been given data of. Then we have this thing called productions and attractions. So every single day, Bankstown is producing 1,000 journeys. 1,000 people are leaving Bankstown. Obviously, that's not true, but... and then every day, 1,000 people arriving in Bankstown. So the implication here, maybe 1,000 people live in Bankstown and they're going to work. But then maybe 1,000 people work in Bankstown, so they're arriving to Bankstown to work. Same with Liverpool, like we got 2,000 people leaving, but then 700 people arriving in Liverpool for work. 3,000 people leaving Cabra for to get to work, and then 6,000 people are coming to go to work in Cabra, or maybe they go to school, other things like that. Okay. Then we have the travel time, and the friction factor. Okay. So the way to think about a friction factor is basically so it'll make sense in a bit, but we have these equations that we're going to substitute all of these values into. Okay, and the friction factor is kind of something that will be inputted into the equation as kind of a calibration thing. So you can see that the friction factor gets lower the higher the travel time is. So it's having less of an impact, which probably, it's not having less of an impact, it's having more of an impact. It'll make sense when I go through the actual equation. But it's kind of a conversion between the travel time and it's like a calibration, okay? Okay, so a trip distribution procedure is carried out using a gravity model, and after the first iteration, the following trip table was obtained. All right, so I will talk through the gravity model in a bit, but I really think it'll help you to actually understand what this means. So this is Bankstown, Livo, Cabra, Fairfield. Okay? Livo, Cabra, Fairfield. Okay, all right, so what we've done, so this is a big part of transport engineering, is we're kind of hypothesizing how many people are going between each of these places, okay? So we know Bankstown is producing 1,000. We know Livo is producing 2,000. We know Cabra is producing 3,000. We know Fairfield is producing 2,200. We don't know where they're all going. We just know 1,000 people are leaving each day. Where are they going to go? Okay, using these equations, we decide, we calculate that 72 people are staying within Bankstown. Because you can you could work in Bankstown, right? You could leave your home in Bankstown and then go to another part of Bankstown. Okay? 68 people are going from Bankstown and then working in Liverpool. 651 are leaving Bankstown and working in Cabramatta. 209 are leaving Bankstown and working in Fairfield. Okay? And then it's the same here. If you read downwards, it's a different thing. Okay? So out of everyone in Cabramatta, 651 are coming from Bankstown. 1,372 are coming from Liverpool. 2,404 are coming within Cabramatta. They're staying there, and 1,657 are coming from within, are coming from Fairfield. Okay, all right. Now what we get is something interesting, which is we actually get that the attractions aren't matching. Okay, so the productions match. Okay, 1,000, 2,000, 3,000, 2,200. They match what we're given here. The attractions don't. Okay, we've gotten the wrong numbers, because this is an iterative process. So you will repeat the gravity model over and over again. In a midterm, she's probably not going to make you do that because that'll take a long time. But that's how you're meant to do it. You would repeat it until you get close enough, okay? So hopefully that makes sense now. I'm going to talk about it more, but I just wanted you to actually understand what the table is trying to illustrate, okay? Now, after the first iteration, the transport modeler decided to update the total attractions using the following adjustment factor, keeping the total production as it is. Okay, so he took the attractions, the attractions observed, and multiplied it by attractions observed over attractions estimated. All right, and we'll talk about that more in a bit. So, this is part A. Actually, I'll read through the question afterwards. Let's go through the theory first, okay? So, this course dives into the four-step model. This is basically how we predict how much traffic will be carried on different roads, and it's very important for traffic modeling. Obviously in the real world, it's just to be honest, I don't work in structural engineering, so I don't actually know. In the real world, you'll just use SIDRA or AIMSUN. You learn about SIDRA if you decide to do CVEN3401 with Divya. It's the same. I'm sure she'll plug it to you guys anyway. This question specifically delves into trip distribution. So we have 4 zones, and we know traffic is being produced or attracted to each zone, but we don't know who's going where, which I already told you. So maybe 50 people are leaving zone 1 every day, but are they going to zone 2, are they going to zone 3, or are they even staying within zone 1? Okay? Now, there are a few methods for trip distribution. There's the growth factor model and the gravity model. The growth factor model is a much easier, but also very simplistic. So I don't really think I've ever really seen that examined. Doesn't mean you don't learn it, obviously still learn it, but gravity model is much more frequent. and obviously much more likely to be examined. And this question will use the gravity model. All right, I'll go over it in a moment. Just take a drink. All right. How far have we recorded? 45. Okay. Cool. So, the gravity model literally uses a variation of Newton's law of gravitation. Okay. So, I'll explain the formula to you. Let's zoom in. So, V equals P times A times F over the sum of A times F. So, V is the number of trips from zone I to zone J. All right, that's what we're looking for. We're trying to figure out how many people are going from Bankstown to Liverpool each day, for example. P is the number of trips produced by zone I, okay? How many trips are being produced by, say, Bankstown? And then A is the number of trips being attracted by zone J. So how many trips are being attracted by Liverpool? So if we're doing Bankstown to Liverpool, how many people go to Liverpool? Finally, F is the friction factor. I was talking to you about friction factor earlier. It's kind of like a factor that you apply that will, in this case, it would decrease the number of trips, okay? Because basically the longer it takes, obviously the less likely people are going to want to go there, okay? So in the case of Bankstown to Liverpool, remember the friction factor, so Bankstown to Liverpool supposedly takes 8 minutes, okay? So if it's 8, that means the friction factor is 0.95, all right? Yeah, so friction factor will either be provided or they'll give you a formula. So they could give you the values or they might just give you a formula to find it yourself. So a quick example so we can get the hang of it. All right, so let's say we've been given these travel times, okay? So we know that the travel time between zone 1 and 1 is 11, zone 1 and 2 is 22, zone 2 and 1 is 16, blah, 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 okay? All right. We also know, so the way to read it is productions are on the right-hand side and then attractions are on the left-hand side, okay? And they should obviously add up to the same number. So obviously, it's just the conservation of mass, right? But applied to transport. Like any cars that are produced also need to be attracted. They can't just vanish in the middle, okay? So in this case, we're going to start with, so we're doing the number of journeys between zone 1 and zone 1, okay? Because there are journeys within the zone, as I've already said. So the formula is P1 times A1 times F11, all right, over the sum of all of the attractions in that zone, okay? So in this case, the attractions are to zone 1. So we do the attractions of 1 times F11, and then 2 times F12, okay? So if we were to assemble it, we know that 3,000 journeys are produced by zone 1, 5,000 journeys are attracted by zone 1. Okay, 5,000? It says 4,000 here. That's weird. Okay, is that a typo maybe? Might be a typo. I think there might be a typo. Because it definitely says 5,000 here. So I don't know what that's about. 4,000. I think that's meant to say 4,000. I think it's a typo. Okay, because yeah, it's definitely a typo. Okay, so 4,000. This is just from the lecture. So 4,000 times 1 over 11 squared, because they've given us the formula for friction factors. Okay. And then we do it over the sum of all of the attractions within zone 1. Okay, in this case, it'll be 1, 2, and also 3. So I don't know. This is quite wrong. Okay, it would also be 3. You would also add. Oh no, there is no zone 3. Okay, never mind. Zone 3 is only producing. Okay, this is a very weird one. Okay, yeah, it's not a typo. This is very strange. I've never seen it be asymmetrical. Usually it would be 3 by 3, not 2 by 3. I don't know why it's like that. But yeah, I think let's just keep going. Let's just go with the actual question. But hopefully that kind of is starting to make a little bit of sense. I will hazard that gravity model is quite tedious. And I don't think you're going to get it just from me explaining it today. I think you will have to go and actually look at it as well. But hopefully this gives you a good foundation with which to understand it. It definitely took me quite a while. I think the main things are productions are on the right, attractions are at the bottom. Might help you to kind of actually name the zones. I think it kind of could help you understand what's going on. Okay, so this question Okay, so part A is using updated, so we're just basically updating the attraction. So part A is actually not even using the gravity model. We're going to do that a bit more later. For now, we just use the equation provided to update the number of attractions. If we read the question carefully, it specifically says the transport, so if we were to go back, I'm not going to go back, but if you look at the question, it says, the transport modeler decided to update the total attractions, keeping the total productions as it is. This means that productions is entirely the same as before. For example, zone 1 is still producing 1,000 trips, so you don't change productions. This column is perfectly the same. Okay, but we are going to update attractions starting with zone 1 attractions. All right, so, okay, this is the formula. All right, so we know, according to this, so this table is our observed table, if you go back to the question. Zone 1 had 1,000 attractions, okay? But when we did our first iteration of our gravity model, zone 1 had 758 attractions instead, okay? So the formula is just 1,000 times 1,000 over 758, and you get 1,319, okay? Great. So repeat it for all the zones, and then you get these answers. Okay. So part A is pretty straightforward. You don't actually need a gravity model for it. You do just need to understand what the estimated and what the observed is, okay? Because otherwise you won't be able to use that formula. Okay. Does anyone need more time on that, or everyone good? Okay. All right, so part B, using these updated productions and attractions, apply the gravity model to determine trips produced by and attracted to traffic zone 3 only. Okay. And this is 7 marks. So you straight away know this is going to take you a long time, and it does. So we're going to have to spend a bit of time on this. So this question is really time consuming. You will not get it right unless you take the time to rewrite everything out clearly and double check your working. So what I've done is I've updated the travel matrix with the new attractions on the left. So before, these are the attractions, and then now I've updated them, and these are the attractions now. All the other values have remained the same. It's just this bottom row is now different because we just did an iteration with the attractions, okay? So now we're going to use that formula from earlier that I took a while to talk about, all right? And we'll go through it slowly, all right? So we're only doing this for zone 3. So let's carefully assemble the values we need to find our first value, V31. Okay, so V31 means from zone 3 to zone 1. So journeys are leaving zone 3 and ending up at zone 1, okay? And you're probably wondering, why are we even doing this? We've already found that between zone 3 and zone 1 is 250. But the point is, well, if you actually add this up, okay, so let's actually do that right now. So 1319 plus 720 plus 5917 plus 369 equals, so if we sum that, it equals 8325. But if we sum the top one, the productions, it equals 8200. So we're getting different numbers. So what we're doing right now is effectively an iteration. We're trying to redo the gravity model. Oh, I think John's out there. That's weird. We're redoing the gravity model as like an iteration to kind of get a more accurate answer. Okay? So that's why, and I think that's kind of what tripped me up about this question as well, because you redo it so that you kind of get a more closer, you get those two numbers to be closer to one another. Okay? Yeah, so let's assemble our values. So first of all, P3 equals 3,000, okay? So we know that zone 3 is producing 3,000 trips, okay? And we also know that zone 1 is attracting 1,319 trips, okay? All right, so that is the numerator, although of course we also need the friction factor, okay? So what is the friction factor for F31? Well, to get between zone 3 and zone 1, it takes 12 minutes, and 12 corresponds to a friction factor of 0.80, okay? Now logically, the friction factor between zone 3 and zone 1 will be the same as the friction factor between zone 1 and zone 3, because it's the same amount of time to travel between both, that isn't always true, of course, because technically like one might be in peak direction, one might not be. In this question, she's kept it simple. It's just, we're just assuming it's the same both ways, okay? Okay. It will also help you to replace the entire time matrix with a friction factor matrix. You don't absolutely have to, but I will for clarity. And you'll kind of understand why in a bit, okay? So the denominator, this is where it gets a bit hard, is the denominator, okay? The denominator is the sum of all attractions multiplied by the friction factor that corresponds to zone 3, okay? And it's all attractions within zone 3, so not within zone 1. This is what really tripped me up. Yep, sorry, yeah?
Sorry, you might have already covered this, but do you interpolate in between those values of friction factor? Like for, let's say we get one for 13 minutes.
Oh, yeah, you would, but I don't think she'd give you that.
Oh.
But yeah, I guess you would interpolate, yeah. But she shouldn't do that. That would be mean. So one thing that really tripped me up was, like, you just really take the time to understand attractions and productions and which one's which. Okay. In this case, we're doing sorry, it'll be zone. Wouldn't it be one? Yeah. Sum of all attractions. Yeah, that's fine. Multiplied by the friction factor that corresponds to zone 3. So be careful about which one it corresponds to, okay? Yeah, okay. Because it would be from zone 3 to zone 1, zone 3 to zone 2. Because it is attracted by zone J, yeah. Yeah, so we're doing from zone 3 to zone 1, and then we'll do zone 3 to zone 2. So really take the time to understand that, because it can be quite complicated, okay? Take the time to actually understand what goes on the denominator. So finally we use this formula, okay? So the formula is the trips produced by zone 3 is 3,000, attracted by zone 1 is 1,319, and then 0.80 is the friction factor. But then the denominator is just going to be this times this, plus this times this, plus this times this, plus this times this, and you should get 325. All right, and you kind of just repeat that for all of them. And this will take you some time to get your head around, but you really just, more than anything, make sure you're multiplying the correct things. Because when I did this last year, I'm pretty sure I stuffed up somewhere like this. So like, you may understand the concept, but the annoying part is which one are you multiplying, okay? So like, make sure you're not multiplying like this one, for example, or like that one. Like, you make sure you multiply the right one. Okay, so I'm not going to go through each and every single one, but you, believe it or not, you have to literally do this 7 times. So it's quite painful. She only told you to do it for zone 3, so this is your new travel matrix, okay? So now, we have 325 trips between zone 3 and zone 1. Before, we had only 250, so it's changed a bit. We had 189 now, before it was 186. We had 2372 now, before it's 2404. Okay, so it's everything's changed a little bit, not like crazy changes, but they've changed slightly. So traffic modeling is not, it's an imprecise science. It's a lot of kind of approximating and a lot of iteration. And yeah, all the x's are missing, but these are the values, okay? Great. Maybe I'll leave it there for a moment. So this, I would definitely say take the time to understand this, because it's quite hard.
So we're just posting these notes on the drive?
Yes, it's on the intro slide. Did you see it? Here we go.
I might have missed it, sorry.
Yeah, that's all right. So the bottom right is this
okay.
one, and then the bottom left is just the midterm.
Okay.
So the bottom left is for when midterms come and you want to practice, which you probably should. That's all right. All right, I'll go back. No. Okay, so this one's easy. The question is, what is the percentage difference between the initial forecasted productions and attractions to the production and attractions obtained after applying the gravity model for zone 3? All right, so first, productions by zone 3. All right, so you see I've summed it, okay? Before we iterated, we had 3,000. After we iterated, we had 3,000, so the percentage difference is 0. Now attractions. Before the iteration, we had 6,000. After the iteration, we had 5,983, so it only went down minus 0.283, okay? But if you remember from earlier, we overestimated the attraction, so we're now closer because it's gone down slightly, okay? So that's good. Okay. We good to move on? Anyone? Yeah, are we good? Great. So now we can move to question 3. So the funny thing about the midterm, and I think one reason why I really got screwed over, so the midterm will be shuffled. Like a lot of Moodle exams, the quiz order will be shuffled. The way mine was shuffled was I got the 2 hardest questions first, and then the rest of it was easy. But I've kept it in the same order because I'm not confident that it was shuffled for everyone, but I assume it was because it was weird that I got the hardest 2 first. It should be easier from now on because I know we've only done 2 questions in an hour, but then like the rest will be much faster. So, a TAS has the following available information presented in Table 1 and 2. Table 3 shows the number of new households to be added in the next 1 year in the TAS. Calculate the total number of trips generated from the TAS. Assume that the current trips remain unchanged. Okay, so the number of households, the number of trips, and then the number of new households to be added, okay? This is by far this is like not just easy, but it's like a type of question where you shouldn't actually even need to, like you should be able to do this without even watching the lecture. It's just like logic. Okay, but I'll explain to you what the question is. Okay, so table 1 is number of households. It's saying that there are, for households that have 2 cars, for households with 2 people but 0 cars, there are 75, okay? There are 52 households with 3 people and 0 cars. There are 12 households with 4 or more people but 0 cars. There are 47 households with 2 people and 1 car, etc., okay? Then, the second table is saying that there are 2,000, so for households with 2 people and 0 cars, all of those households made 2,043 trips, okay? Weirdly enough, for households with 2 people and 1 car, they made less trips. They made 1,977. In fact, this is a very weird table. It seems like the most trips were made by... Oh, no, I see why. It's because there's the most households. It's because it has 75. So yeah, okay. And then table 3 is the number of new households to be added. So we're adding 91 new households with 0 cars but 2 people. And then, like, for example, this one is we're adding 47 new households with more than 2 or more, but then 4 or more people as well. Okay? All right. So, yes?
Sorry, when you say trips, does that mean like public transport and cars or just...
It'll probably mean anything.
Oh.
Yeah. It would have to mean public transport because
Yeah, say no car.
they don't own a car. Yeah. Yeah, it would mean any sort of trip. All right. Let's check we're recording. We've done an hour now. Okay. A TAS has the following information available, presented in tables 1 and 2. All right, we've already read this. Okay, so this is a trip rate question. TAS means traffic analysis zone. Okay, you can just say TAS. First, figure out the trip rate. For example, we know there are 75 households with 2 people and 0 cars. And out of these households, they generate 2,043 trips. Okay? So that means that each household is generating 27.24 trips. Okay? 2,043 trips, there are 75 of them, so that's how many they are generating. Okay? I think this is per year. I don't know. Yeah, and then if you repeat it for all of them, these are the trip rates. Okay, so for example, households with more than 3 people and more than 1 car have 22.63 trips generated. Okay, so that's how many they generate on average. Or trips with 3 people and more than 1 car generate 51 trips. That's crazy, but yeah. Okay, now we can figure out how many trips the new households will generate. Okay, and I might need to start talking quieter because my voice is like dying. Let's see if I can turn the mic on. Is there a mic? More inputs. Okay, I don't know. Volume control? Okay, it's not a big deal. All right. Oh, no, there is. That's not on there. Anyway, it's okay. Let's go back to room control. Okay, so now we can figure out the number of chips that the new household will generate. Okay. So there are 27.24 per household, and there are 91 new households to be generated. So that ends up being the new households will generate that many trips. In this case, they'll generate that many trips. Blah blah blah. Okay. Pretty straightforward. It's just like matrix multiplication. Good thing is this exam's online. I highly encourage you to use highly encourage you to use Excel spreadsheet for this one. There's no reason to do this manually. Oh no, you should. Sorry, because she marks working out. You could still do it in Excel, but you would need to include a screenshot if you're using your iPad, and if you're using written, then you may as well just do it by hand. It could help you to do it in a spreadsheet to check your answer, and then you can just copy it in. That's what I would do, because then you know you're correct. Right? Now, then you add this number to the number of trips previously. Okay, so we originally had 2,043 trips. Now new trips is 2,479. Add them all up, 4,522. Add all of these up, and you get 38,734. Okay, that's how many trips are generated. That should hopefully make sense. Any questions? All good? No, great. Yeah, so question 3 is quite straightforward, and it's an easy 6 marks in my opinion. Question 4, sorry, that was question 3. Question 4 is also quite straightforward, not as, you still need a bit of theoretical knowledge, and the previous one you kind of could just do it, but this one you need a bit of knowledge. So, consider the network below, a bit of a weird one. So, I think I'll actually explain the theory behind this first, but I'll read it out to you, okay? So, actually no, I'll explain the theory first. Okay, so, this is a trip assignment question. Users make their own travel choices, which are approximated by the provided equations. And this question is straightforward since we are assuming the roads are all empty. Yeah, so basically, alright, so how does this work? Oh, that's weird. I haven't got an explanation slide for some reason. Okay, so basically, T1 equals x1 plus 3. T2 equals 2x plus 2. T3 equals 3x. T4 equals 20. T5 equals x. Okay, x means how many cars are there on the road, and t is the travel time. So in other words, if you have one car on the road, the first part, T1, will take 1 plus 3, which is 4 minutes. The second part will take 2 times 1 plus 1, which is 3 minutes. The third part will take 3 times 1, which is 3 minutes. The fourth one just takes 20 minutes no matter what. And then the fifth one will take 1 minute, because there's one car. Okay? It's a very, very simplistic representation of roads. Obviously, like, it's not like if there's one car, it'll take 1 minute, and then if there's 2 cars, it'll take 2 minutes. That's like ridiculous. But like, it's just a theoretical thing. Okay? It's meant to illustrate to you user equilibrium, although that's actually question 6. But anyway. Okay, so basically we're trying to just figure out what's the fastest way to get from 1 to 4. Okay? Now, T1 is, so we're assuming all the roads are empty, okay, for the first user, okay? Actually, no, wouldn't it be, I actually think it should be 1. So I think we actually meant to take x to be 1. I don't think it's meant to be x is 2, so it's 0. So it actually be, I actually need to correct that. So it'd be 1 plus 3 equals 4. It'd be 2 times 1 plus 1 is 3. 3 times 1 is 3. It shouldn't change the answer though. And this is 1. Okay, so this ends up being 4. This, which one was, that ends up being 3. That ends up being 1. That ends up being 3. And then that's still 20. So it's still the same answer. Okay, but that's just like a minor correction. Because now there's one car on the road. Okay, so basically, okay, so what I've done is I've matched it to this. Okay, so T1 is this. T2 is this. T3 is this one, T4 is this one, and then T5 is that one. Okay, so, and I've matched it all up, all right? So, it's 1 to 4, so 1 to 4 is like that, okay? Yeah, so that's why that's the fastest. And it can't be like that. Actually, that's no longer even relevant anyway, because that's no longer the faster one. But that's because the arrow is pointing the wrong way, okay? Yeah. All good? All right. Making good time. So question 5 is a little bit harder. It's still easier than the last few. The big 2 at the start, I mean. Okay, I can't move that. All right. So a binary logit model has been formulated to describe the mode choice of a community between private automobile and bus utilization. A survey of travelers in the community regarding their travel experiences yielded the following data. Okay. The calibrated utility function is defined as UK equals AK minus 0.10x1 minus 0.13x2 minus 0.12x3 minus 0.0045x4. Okay, so basically, part A is asking us how many people what's the mode split between the car and the bus? Okay, what percentage of people are taking the car? What percentage of people are taking the bus? And part B is asking us, well, okay, it turns out now it takes 10 minutes longer to take anything. Okay, both of them take 10 minutes longer, but also cars now need to spend an extra 5 minutes parking. So what's the new mode split? Part C is we've now implemented some improvements and we've gotten, so we're actually told the mode splits, we just need to work backwards to find, so we're working backwards to find the calibration constant for buses now, okay? Yeah. Okay, so I'll kind of talk you through the theory behind this. It's quite doable. Out of anything, I think you can hopefully try and understand this today, if you can. All right. So to understand this question, we must learn about utility equations. These equations assign utility values to different modes of transport. This is done by assembling different characteristics of transport, for example, travel time, parking time, walking time, and so on. Okay? Yeah. So UK equals AK minus beta K times cos Tk plus gamma K times the level of service K minus, what is that symbol again? Omega, I don't know. Times, yeah, so they're different variables, okay? So I'll kind of talk you through it. So the parameters may or may not vary, usually they don't. They're like the coefficients assigned as a sort of penalty or benefit. So I'll go through an example afterwards. And then the variables are what actually change between each mode. Okay, so for example, the bus takes longer usually, so the travel time will go up. There'll also be an alternative specific constant, or you may also know it as a calibration constant, and that exists to resolve unobserved preferences that the model may not be capturing. So for example, if everyone wants to take the bus, they might make the calibration constant higher, and they may not know why everyone's taking the bus, but they just make it higher to kind of like account for that, okay? The higher the utility UK, the more likely customers are to use it. So, for example, take UK equals 0.8 minus 0.4t minus 0.5c. All right, so we're saying t is travel time and c is cost, okay? We're applying a factor of 0.5 to cost and 0.4 to time. So, for example, if you have a really high travel time and a really high cost, your utility is going to be very low, right? If you look at that equation, that's going to get really low. But if you have a really low travel time, so it's really quick, and a really low cost, then obviously the utility is going to be higher. So it's very straightforward. It's literally the lower UK is, the worse it is. The higher UK is, the better it is. Okay? So for example, let's say we have a bus journey and it takes 10 minutes and costs $2, while the car takes 5 minutes and costs $5. Okay? So you just plug in those values, and the bus will be taking minus 4.2. Sorry. The bus, you end up with a utility of minus 4.2, whereas the car, you end up with a utility of minus 3.7. Okay? So which one's lower? You end up with the car having a higher utility. Okay? So the car has a higher utility, so we're more likely to take the car. Okay? Hope that makes sense. Okay, so bus. Okay, so in this question, oh yeah, we're not doing the question yet. This is still my example. Okay. So we're saying that U-bus in my example is minus 4.2 and U-car equals minus 3.7. Here's the thing, what does that mean? If I tell you the utility of the car is 3.7, like what on earth does that mean? Like no one's going to know. Like that just is a unitless value, it's useless. But mode share split does tell you something, okay? If I told you 80% of people are taking the bus, you're like, yes, I understand what that means. So this is all about converting it into that, okay? So we can process this further to develop a mode share split, which will tell us what percentage use the car and what percentage take the bus. All right, and we're going to use something called a multinomial logic model. All right, and this is the formula. So the probability of you taking that mode is going to be e to the power of its utility over e to the power of all the utilities. Okay, like e to the power of the bus and then add e to the utility of the car. Okay, so going to be the sum. So for example, in this case, the utility of the bus is e to the minus, the mode share of the bus is e to the minus 4.2 over e to the minus 4.2 plus e to the minus 3.7. And for the car, it's e to the minus 3.7 over e to the minus 4.2 plus e to the minus 3.7. Okay, it's meant to be a dot there, sorry. Yeah, which equals, so this in this case it's 37.75%, in this case it's 62.25%. Okay, and that is the mode split. All right, so now we can actually do the question. Okay, so it's quite straightforward. Remember the multinomial logic model. So, to be honest, I think it should already make sense because I did them. But basically, this is our equation. It's UK equals AK minus 0.10x1 minus 0.13x2 minus 0.12x3 minus 0.0045x4. All right. So minus 0.33 minus 0. So you just plug. Look, honestly, just plug in all the values. It's not that hard. For the car, you get minus 4.655. For the bus, you get minus 6.27. Okay? So what does the probability that you take the car end up being? It's 83.4%. In other words, there is an 83.4% mode share. That is what percentage of people are taking the car. Whereas the bus, if you do the same thing, because we got a much lower utility, so unsurprisingly, we get a much lower mode share. And you get only 16.6%. Okay? Part B is quite straightforward. All that's changed is travel time is 10 minutes longer for both, and parking time is 5 minutes longer for cars. Otherwise, our calculations are identical. So if you look at my equations, I've just added 10 to the time, and I've added 5 to the car parking. All right, and you should get that mode share. You get 73.4% of people take the car, 26.6% of people take the bus. All right, any questions? All good? Okay. So now, if you understand part A and B, part C is not very hard, okay? After implementing service improvement to the buses and the road network, the parking time and travel time return to the original values for both modes. So we're now resetting and we're using the part A values, okay? So we're using using all of this, okay? In addition, as a result of the service improvements, the mode split was observed to change to 81.6% private automobile and 18.4% bus use. Determine a value for the calibration constant for the bus mode that reflects the shift in mode split. Okay, so the wording of so basically, we assume we have given the mode share, okay? And we're told we're basically, the way it's worded is we can assume that car is unchanged. Okay, the car still has a utility from part A. In part A, we figured out the utility of the car is minus 4.655. Okay, so what is the mode split of the car? Well, it is e to the power of minus 4.655 over e to the power of the utility of the bus plus e to the minus 4.655, which equals 0.816. Okay, because we're told the mode split of the car is 81.6%. Okay, and then it's literally just logs. It's literally just solving this equation. Okay, and so what we end up with is so you just flip that, multiply that out, take that to the other side, and then take the log of both sides. Okay, I think I'm not going to go through how to do logs. I think you guys should know how to do logs. Okay. But the question isn't asking us for the new utility of the bus. Okay, so like anything, like any subject, like maths, like everything, just make sure you read the question. It's asking us to find the calibration constant, okay? So plug utility of the bus back into our equation from part A. we're assuming all the values stay the same except for the calibration constant. Okay, so minus 6.1445 equals the new calibration constant, and then all of these values. Okay, and you should get the new calibration constant to be minus 0.1445. And that is question 5. Just one more layer. All right. So now question 6. There are 3 routes available to travelers between a single origin-destination pair. For each case below, you are given the travel time t on each route, as well as the number of travelers x using each route. Select the case that satisfies the principle of user equilibrium. Okay? To do this, I need to explain to you what user equilibrium is. Okay? So, Wardrop's user equilibrium principle states that the travel time on all routes used are equal. Okay, so if a route is being used, the travel time is equal. And the travel time on any used route is less or equal to the travel time that a traveler would experience on any unused route. What that's saying is, I'm not going to use the route that takes me 20 minutes if the route that takes me 10 minutes is available. Okay? So let's look through all the options. Okay, so option A is route 1 takes 30 minutes. Route 2 takes 40 minutes. Route 3 takes 30 minutes. All right, 0 people are using route 1, 25 people are using route 2, 0 people are using route 3. Okay? So, route 1 and route 3 take the same amount of time. And yet, according to part A, everyone is taking route 2 even though route 2 takes longer. That is not user equilibrium. That's stupid. Like, no one's taking any of the other routes. Okay, so we eliminate route A. Now, option B, 25 people are using, route 1 takes 25 minutes, route 2 takes 30 minutes, route 3 takes 30 minutes, okay? 0 people are using route 1, 40 people are using route 2, and 35 people are using route 3. Route 1 is the fastest, and yet people are using route 2 and 3 for some reason, okay? So it's obviously not B. In option C, 45 people use route 1, 35 people use route 2, 30 people use route 3. Route 1 takes 45 minutes, route 2 takes 35 minutes, route 3 takes 30 minutes, but only 10 people use route 1, only 25 people use route 2, no one uses route 3. But route 3 is the fastest. Okay, so why is no one using route 3? We don't know. Okay, so it's obviously not option C. Finally, with option D, well, we obviously know it has to be option D because none of the others were right, but route 1 takes 10 minutes, route 2 takes 30 minutes, route 3 takes 45 minutes, 50 people use route 1, and no one's using the other 2. That's finally what we want. Everyone's using route 1 because route 1's the fastest. So a better way to phrase this question is like, which one makes the most sense? Which one is going to keep people happiest? Obviously, it's the one where everyone's using the fastest route, okay? So that's the midterm over. I have more questions. If you want to leave, I guess you can, but I do have more. Yeah, but that's the midterm. So if you can get through that, then you should be set. I definitely advise you to take a lot of time to understand Greenshields model and trip generation, because those two are quite difficult. User equilibrium is relatively straightforward. Utility equations, it's not like, it's pretty hard to make that hard. There's only so much you can do to utility equations to make it challenging, so those are pretty straightforward. But trip distribution will take a while, like gravity model, will take you a while to wrap your head around, so spend the time on that, okay? So for the second half, anyone here do Enviro, or we just have Civil? All right, okay, that's fine then. So the second half of the course is actually different for Enviro. That's why this course is called Sustainable Engineering, Sustainable Highway Engineering. I don't think it's a good name for the course because the civil component is not very sustainable. I think the Enviro component is probably why they call it sustainable. The civil component is just normal. It's just normal highway engineering. All right? We don't learn any sustainability. So in this crash course, I've mostly just discussed the first half. That's because the second half is 5 weeks away. You're probably going to forget it all. I don't think there's much of a point. The entire first half of the course, stream 1 is done by both civil and Enviro, and then stream 2 is where you'll split off. So everyone here sticks with Divya. Stream 2 I don't know what her name is, but it's a different lecturer. But it doesn't matter because no one here does Enviro. People are watching online, sorry any Enviro engineers watching. But you guys will split off to another lecturer and I don't know much about the Enviro component, so this is where you can probably stop watching the video. Stream 2 is full of what you'd imagine a highway engineer does. So Stream 1 is like, if you work in transport engineering, like it makes sense, but Stream 2 is like what you would stereotypically imagine a highway engineer does. Like, it's about measuring roads, it's about crests and dips, it's like how much bridge clearance do we need, what's the radius of the curve. I would argue if like your interest is like structural engineering and you have no interest in transport, you'd probably enjoy the second half of the course more. If you want to do transport engineering, then you'll probably just enjoy all of it, to be honest. I would say the first half of the course is what the electives expand on more. Like in the last lecture last year, Divya told me and a bunch of others that her specialty is the first half of the course, and then the second half of the course she just has to teach because it's an Engineers Australia requirement. And having done CVEN3401, I would agree with that because she definitely, CVEN3401 is way more about the first half of the course. Anyway, so yeah, second half of the course, a lot more stereotypically engineering stuff. Okay. Stream 2 was, what is this? Oh, right, I forgot I had another QR code. So Stream 2 was a take-home, entirely open book assignment, which made it much easier, but even then, everyone's numbers are different, so you still got to understand the content. You can't just copy your friend's stuff. It's good revision for the final as well. So we'll go through just a few questions. It's actually, I'm only ended up having time to go through 2, but I think that's perfect because we only have 20 minutes left anyway. And then these are the formulas. They should be on your Moodle, but I don't know if Divya's made it public yet, so I've just got it there if you want. Yeah, okay. Okay, so this is just 2 questions. I didn't have much time. I just did this. I did the rest of it on like Friday, and then this I did this morning. So a driver is traveling at 95 kilometers an hour on a road. An object is spotted on the road 145 meters ahead, and the driver is able to come to a stop just before hitting the object. Assume 2.5 seconds for reaction time and 0.36 for longitudinal deceleration. Determine the grade of the road. Okay, this is a great warm-up question. Okay, so this is a warm-up into the concept of stopping sight distance and reaction distance. Okay, and if you guys like tables, which is, I don't know if anyone likes tables, but if you do, the second half of the course has a lot of tables, so you need to kind of understand all the tables. All right. So what is stopping sight distance? Well, think about it. If you're driving and you see, like, maybe like you're out in the countryside and the kangaroo jumps onto the road, right? Like, if it jumps in front of you far enough, you might have enough distance to stop. If it jumps right immediately in front of you, you will probably hit it, okay? Theoretically, there is a certain, like, you can measure the minimum, the absolute minimum at which that kangaroo can jump in front of you. That allows you to stop in time, okay? That is the stopping sight distance. It's the minimum distance between a car and an obstacle for a car to have enough distance to safely stop, okay? But there's a lot of consideration. So obviously, stopping sight distance goes down if you're going slower. If you have a sharp reaction time, obviously it'll go slower, it'll go down as well. But a lot like structural engineering, a lot like steels, you kind of assume the worst case scenario, okay? So the formula is reaction time multiplied by the speed of the road over 3.6, because the speed of the road is in kilometers per hour, so that's why we divided by 3.6, plus the speed of the road squared over 254 times d plus 0.01 g, okay, where d is the coefficient of longitudinal deceleration and g is the grade. Okay, so we are given the reaction time here, but in the next question, which is the last one, so this is the second last question, there's one more after this. In the next question, we're not given the reaction time, okay? So I would recommend always just take the worst case, okay? So let's have a read through these. So these are the in that QR code I provided earlier, this is one of the tables, okay? And this is Austroads. So for anyone who wants to go into transport engineering, Austroads is like the people who kind of manage all the standards of highway design and traffic modeling and everything. And you come across it over and over again in your career if you go into transport engineering, okay? So driver reaction times, all right. So a reaction time, so let's say 1.5. So that's like the most optimistic. You took only 1.5 seconds to react, okay? That means it's alert driving conditions, okay? Maybe you're driving on a local road like Anzac Parade, okay? There's lots of traffic lights, so you're reacting quickly, okay? Because, like, I don't know if people here drive. Does everyone drive? Anyone not drive? You know, it's not a big deal. But like, if you've driven in the countryside, like if you've driven on the Hume Highway or the Pacific Highway, like you can probably remember, like you kind of zone out, right? You kind of just go into autopilot. But if you're driving here, like on Anzac Parade or in the city, like you're on high alert because it's like much more stressful, right? So that's the 1.5 seconds is the absolute minimum that we can assume. 2 seconds is kind of a good middle ground, and then 2.5 is the worst case, all right? And that's what we want to design for usually. Okay? This question is quite straightforward because we're given all the numbers. And I even went to the liberty of drawing. This is actually my assignment. This is what I submitted that last year. So we're told the reaction time is 2.5 seconds. We're given a grade of 1% grade. D is 0.36, and the vehicle is going at 95 kilometers an hour. Okay, so the stopping sight distance is RT times V over 3.6 plus V squared over 254 times D plus 0.01 G. Okay, we will assume SSD equals 145 meters. Oh, right, we're trying to find the grade. Yeah, I forgot about that. Yeah, sorry. I thought we were finding the stopping sight distance. My bad. So we're assuming that 145 meters is the stopping sight distance, okay? So we're assuming it's going to stop right before. Okay, this is a working backwards question. So you just plug all the numbers in. We're looking for G. So sorry, when I said the grade is 1%, I was misreading it. The grade is not 1%, so ignore that. The grade is unknown. The 0.01 is just what you put in front of the grade, okay? Yeah, so you solve all of this. I shouldn't have to really go through that. Like, you just will look through my working and it should make sense. It's just a lot of changing the subject, and you should get that the road has a grade of 8.961%. And it's asked for 3 decimal places, I think. So, yeah. So this is just a nice warm-up. Any questions on that? All good? Nice. Okay, so thank you for your patience. There's just one more question now, and then we can finish up. So this one is a pretty big one. I'll read through it. So basically, a tunnel at level grade has a design speed of 105 kilometers an hour and curves with radius 950 meters. The tunnel is situated in an urban area with 1 lane in each direction. Each lane is 4 meters wide and the sidewalk is 2 meters wide. So we've seen there's a sidewalk on both sides. Okay, determine an appropriate super elevation rate for the circular curve. And I'll explain to you what super elevation is in a moment. And then we also find the coefficient of side friction. Then check if the available sight distance exceeds the stopping sight distance. Okay, which again, I'll explain that to you in a moment. And then part C, we don't end up needing part C, but you'll see why in a moment. Okay, so first of all, you want to know what super elevation is. Okay, so super elevation is the amount by which the outer edge of a curve on a road is banked above the inner edge, and it's measured as a percentage. For example, E equals 5% means that for every 1 meter along the road, there is a 0.05 meter increase in elevation of the bank. Okay, so this one is not as obvious in local places, but when you're out in the country, it's really obvious. So the next time you're hopefully you're not going at 150 kilometers an hour, but if you are, pay attention to how the road banks. Okay, so like I say the Princess Highway because it's a very windy road. So if you're ever down south, it will bank at certain turns. It actually you guys know this because we all did banked tracks in high school, but we're like kind of diving into the nitty gritty now rather than just being like, when we do banked tracks, it's not like this, okay? We're now actually designing the banked track itself. Okay, so this is the equation for the super elevation rate, okay? So we're finding E1, it equals the speed of the road squared, where speed is in kilometers an hour, multiplied by the maximum super elevation allowed, okay? And then the denominator is 127 times the radius of the curve, all right, and then that's times the maximum of super elevation plus the maximum coefficient of side friction, okay? And we got to get a lot of this from the tables, which is why that document I showed you earlier is very important, okay? So, all right, so there's a lot of values that we need to get. So first of all, we want the minimum radii, because if you look here, R, okay, the curve radius needs to be greater than minimum. Okay, so this gives me a lot of Steele's flashbacks where it's like you kind of need to and not just Steele's concrete or structural, like you need to check, you need to make sure minimum values are fulfilled, maximum values are fulfilled, blah, 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 okay? In this case, the table 7.6 tells us that Actually, we'll do R later on, sorry, because R we need to find F max first. Okay, so let's find F max and E max first. All right. So E max is table 7.8. Okay. Now the question tells us we are in an urban situation. Okay. That means we can't have a super elevation higher than 5%. Okay. If the super elevation is too high, then it's too uncomfortable to go at a slow speed. Okay. And then we want F max. All right. So so this is where it's a bit challenging because the question says 105 kilometers an hour, which I don't know why, because there's no road in the world, or at least in Australia, where you're going at 105 kilometers an hour. But fortunately for us, there's no interpolation involved because the F max is going to be the same. Because for 100 kilometers an hour, it's 0.12, and for 110 kilometers an hour, it's also 0.12. Okay, so F max is just 0.12. Right. So we now know E max is 0.0 is 5%, and F max is 0.12. Okay, so we look at this table. Firstly, we're doing an urban road. We've said E max is 5%, and our operating speed has been between 100 and 110. Okay, it's 105. And you might be thinking, wait, are we using design minimum or absolute minimum? We're using design minimum, but the thing is it actually doesn't even matter because there's no value provided. And you might be panicking. You might be like, why is there no value provided? The reason no value is provided is because there is no radius maximum. Okay, we're going fast enough that we don't have to worry. Minimum. There's no minimum radii, so we don't have to worry about it. Okay, that's why there's no value there. Okay, yeah. So now we can plug all our values in. Okay, so E1 equals 105 squared plus 0.05. So it's not 5, it's 0.05, like any percentage. Over 127 plus 950, because 950 was the radius. Times 950. And then times, you are?
Yeah, 4. The next one, study last 4.
What's that, sorry?
It's come 11 and 20.
This is a different thing. Is that at 4 o'clock?
Yeah.
Oh, okay. We haven't started. That must be next. We will have, yeah. Sorry. I guess we'll have to leave. All right. Better wind up then. I guess there's something after this. Okay. Yeah, where was I? Okay, and then F max, so 0.05 plus 0.12. Next, we want to find the coefficient of side friction. This is a dimensionless value that is used to ensure cars can safely navigate curves without skidding. All right, and that's the equation. F1 equals V squared over 127R minus E1, but E1 is rounded. Okay, so we don't just use this value, we round it to the nearest 0.5, nearest 5%. I think it's 0.5%, sorry, that's a big typo. I need to fix that. 0.5, I'm gonna fix these notes and then update it. Okay, there you go. So it's the nearest 0.5%. Okay, yeah, so in this case, Divya's notes, it's ironic because her notes were wrong, but then now my notes are also wrong, but I'll fix that up. Basically, she didn't make it clear, maybe she'll change it this year, she didn't make it clear you round up. So she just said round it to the nearest 0.5%. You need to actually round it up, so it becomes 3%, okay? And then you end up with 0.061. Now, fortunately for us, 0.061 is less than the maximum. We got an F max of 0.12, so we're fine, okay? Because remember from the tables earlier, we decided F max is 0.12, and our F is lower than that, so it's fine. All right, so I'm going to keep going. We're really, really close to the end, so we can finish up in 5, and then we can have a bit of time to pack up before the next class. All right, so part B is check if the available sight distance exceeds the stopping sight distance. Okay, so here's the thing. Before, we were just assuming it's a straight road, but now there's an actual curve in the road, and that's not good. Because if there's a curve, think about a curve, like you won't be able to see ahead of you for the whole curve. So you actually need to work out what the sight distance for the curve actually is, okay? And this is the equation to figure out how far in front of the curve you can actually see. So S equals RV times pi over 90 times cos to the minus 1 RV minus M over RV, okay? Where R is the radius to the center line of the road, RV is the radius to the center line of the inner lane, and M is the distance of the obstacle to the center line of the inner lane. All right, and then after this, we make sure that S is greater than a stopping sight distance. obviously what you see needs to be greater than the stopping sight distance, okay? Because if it's less, then you're not going to stop in time, okay? So I've kind of drawn this out. I might kind of gloss over it so we can finish up a little bit faster. But basically, I've drawn it out. So the radius that we've been given is to the center of the road, which is here, okay? The center line of the inner lane is here, so it's 2 meters lower. And then the obstacle in this case is the actual tunnel itself, all right? It's the tunnel, okay? Yeah, so you end up with RV equals 948 and M equals 4. So you end up getting an S of 174.234 meters. Then we find SSD as per before. We have to make some assumptions this time. So we're going to assume RT is 2.5. I was talking about reaction time before. This time we don't take D to be 0.36, all right? I took it to be 0.36 when I did the assignment. It's actually 0.46, okay? Because what the table says is you use 0.46 in constrained locations. And look, one of the constrained locations is a tunnel. So we use it in this case because it's constrained, okay? And the grade is 0%. All right, so you end up with a stopping sight distance of 167.276 meters. Luckily, our sight distance is greater than our stopping sight distance, therefore it's okay. And this curve is safe. And part C is not required because the curve is safe. Part C was find the stopping sight distance. Yeah, all right, so that's the whole crash course done. Any questions? All right, so my general advice for this course is to definitely give it enough attention because it isn't the easiest. But, you know, if you watch my crash course, if you go through this midterm, you should be all right. Great. All right, and thank you all for coming. Great. It's all right.